Hello. You have... I can't believe I'm talking to a cat. I mean, is it really going to understand me anyway?
Gary, just read the lines.
Fine. Hello, my furry friend. You have been selected to play a key role in an upcoming physics experiment. Since the theory of quantum mechanics was first described, humanity has been seeking to discover what exactly happens when a quantum superposition ends. In this case, the superposition of a radioactive particle. The standard view of quantum mechanics is the Copenhagen Interpretation, and I've been told that, as our test subject, you need to have a basic understanding of what this is. What you need to understand is, what things are when we measure them is fundamentally different to what they are when we are not measuring them. A radioactive atom, in isolation, has an unpredictable chance to decay and release radiation into the environment. When the atom is being measured, it is clearly in one of these two states, decayed or stable. When left without any interaction from its environment, the atom remains in a superposition, meaning that it does not have a definite state until it has some form of interaction. This means we cannot measure a particle in the superposition without disturbing it. Any measurement, such as hitting it with light, causes the superposition to collapse because it's then interacting with its environment. I must stress that this is not the same as ignorance. When your caretaker opens a tin of unmarked cat food, one could say that the contents could be anything, because you personally don't know what it is. This is not what is happening with particles in a superposition. The cat food in the tin is and always has been the food that you will eat. Timmy's fabulous cat food for good kitties. It is possible, however, to calculate the likelihood that the particle will collapse into any given state. A wave function is a mathematical description of the properties associated with the particles collapsing into one of the states described by the superposition. Wave functions also take into account variables such as the passage of time. So in short, a superposition describes a system existing in multiple states at once. The wave function mathematically describes the probabilities of each outcome. When the Copenhagen interpretation of quantum mechanics was first proposed, Erwin Schrödinger created a thought experiment to demonstrate the foolishness of thinking about quantum states for large objects. He proposed the following scenario. A cat is locked in a steel chamber. In the chamber is a radioactive particle. Over the course of an hour, there is an equal chance that the particle will decay and that it will not. If it does, a Geiger counter will detect this decay and release a hammer that will shatter a small flask of hydrocyanic acid, which would kill the cat. So the cat would live if the atom remained stable, and it would not if it decayed. This, in theory, would cause the cat state to be indeterminate, as this is entangled in the wave function of the radioactive atom. Schrödinger didn't like the Copenhagen interpretation, and proposed this experiment to challenge other scientists' assumptions about the theory. However, scientists have since been able to place particles in superposed states. While the cat is not exactly dead and alive at the same time, as you may have heard, the thought that the cat's death is indeterminate doesn't really make sense in classical physics. And the reason that we don't see quantum states like this in real life is because macroscopic objects big enough to be seen with the naked eye, are constantly interacting with their surroundings, which prevents superpositions from being sustained for any meaningful period. We, at the Many Worlds Institute, think we have found a way around this macroscopic issue, and so we'll be conducting this thought experiment as an actual experiment, with you, my little friend, playing the part of the cat. Whilst I'm not entirely sure why my colleagues think that you will understand all that I've said to you, you are about to embark on a journey to help modern science understand one of the most puzzling and decisive questions known in recent years. Oh, and by the way, still debating what exactly causes a wave function to collapse. Any interaction that allows information to spread to the environment can do it, so try not to interact with anything too much or you'll ruin our experiment. If you would now please go through the door marked lab to begin the experiment.